was true here, right? Making this smaller by replacing epsilon by epsilon squared preserved the less than. This time we're going in the opposite direction. So what do we want to have happen to this thing in our next line? No, actually, because we'll still be in trouble if we do that. We can't assume epsilon is bigger than 1 anyway, right? Because it has to be true for all epsilon, meaning all small epsilon. Sorry, we're trying to find an epsilon, but yes. Okay, let me back up. We're trying to find an epsilon here, and why can't we choose epsilon bigger than 1, actually? There's a reason. I mean, that was a good suggestion at first, but there's a reason why we can't do that. We need that. But there's a simpler way. I mean, there's a simpler way to do this, right? And plus, also, there's another reason for it, because eventually, as you'll see, we're going to have to make epsilon less than some other quantity. And you're going to have a bigger than and a less than quantity. So we got a couple of things we're trying to make epsilon less than. And if we make it bigger here, then that throws everything out. And so even though that's maybe a good instinct, it's symmetrical to what we did before. Remember, when you're trying to find these epsilon, usually the epsilon has to be very, very small, right? In order for this to work. As you already know, a big epsilon isn't going to work. So what you want to do is make epsilon small. And in fact, there's actually an easier strategy now to make this smaller. Okay? And what's that going to be?
Just get rid of 2s epsilon.
Just throw away epsilon squared. Just throw away the whole thing. Let's see if that works. If this one is bigger than A, this one here is even bigger than that one. So if this is bigger than A, then adding the epsilon squared is still going to be bigger than A. Logic does not go this way, but it does go this way, and that's what matters. Okay, so we didn't like epsilon squared. Okay, we'll just throw it away. And that's where inequalities are often easier to deal with than equalities. And that's why very often when you're trying to prove things in analysis, instead of trying to prove A equal B, you will try to prove A less than or equal to B and B less than or equal to A. Because inequalities often give you some maneuverability. Okay? And so now we're in good shape, right? Because we can kick the epsilon over there. And that's another reason, since we have a minus sign here, that's another reason to realize that we're going to have to kick epsilon to the other side, and when we do, it's going to be less than. So that's another reason why we wouldn't want to take epsilon bigger than 1. Because then again, we're going to have things which, inequalities going opposite directions that we won't be able to work with. Okay, so again, the idea, just keep in mind, epsilon, in these situations, epsilon's got to be small. Smaller than this, smaller than that. And you usually want to get finitely many things that epsilon is smaller than, right? And then you're usually good, right? That's the way these arguments often go. Okay, so less than, let's see if I can do this. So this is going to, so we're kicking this, that, okay, so it's s squared minus a over 2s. Now, what do we need to be able to pick such an epsilon? What do we need to know about this quantity? It's where I last time realized suddenly that the minus sign was incorrect because it didn't work, right? But what do we need to know about this to be able to choose such an epsilon? What do we need to know about this? Well, or the same sign anyway, right? Okay. But it is positive, right? Because what case are we in? S squared bigger than A. So this is positive. S is, even bigger than 1. We know that, right? So that's positive. So this is positive. Okay. Now, this is the calculation. This tells us how to pick epsilon. All right. And so now we'll just go back and work it out. So having done this, you could even just erase this, right? But not before you write down. So we're going to choose epsilon bigger than 0 such that epsilon is less than the minimum of, okay, we also needed s in there, right, in order to get this part to work. And then we need this thing here. Okay, and since epsilon is less than s, we get a contradiction as in our little star there. Okay, so that's what we needed for our contradiction. And then, provided we could verify this, so let's just start. Well, might as well just erase this now because you really don't want that as part of your proof anymore, or you're going to have to, you know, explain to me what the logic is and all that, right? And that's more work, and it's also safer just to check. So let's start it. So s minus epsilon squared is equal to s squared minus 2s epsilon plus epsilon squared. And now here's where we do our throwaway. So, right, this is bigger than s squared minus 2s epsilon. And now we want to replace epsilon with this one. Now, it's important that the inequalities go the same way, right? If there's anything reversed in there, it's all nonsense, right? So why does the inequality still go this way? We got epsilon less than this. Why do I get greater than here? What's the thing in there that does that?
Because it's making the 2s epsilon turn bigger, and you're subtracting
Negative. Yep.
the bigger number.
Got a minus sign in there. So really what you're using, epsilon is less than that, but minus epsilon is bigger than minus that. So when I make this replacement of epsilon, my inequality goes the right way. And do you see how, you know, everything now is lined up, and the minus sign helps you. Even though you've made epsilon small, because of the minus sign, you now make things bigger. And that's yet another reason why it was good to get rid of that, right? Because that would just confuse things. So this is now bigger than s squared, not equal, of course, right? But it's bigger than s squared minus 2s times s squared minus a over 2s. And now cancel, 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 a. Okay? So once again, it would not be incorrect to leave that calculation and carefully tell me why the logic goes uphill. But there are so many opportunities to make mistakes when dealing with inequalities that you should just get into this habit of checking your work when you're done with one long inequality. Yes?
Where does your negative go on the A?
The negative of a negative.
Oh, okay, I see. Gotcha.
Okay, questions about this? Yes?
Why can we say that the epsilon is less than the minimum of those two?
We're choosing it. And so, question, this is a question, right? Why can I choose epsilon less than the minimum of those two? Well, this goes back to that lemma, right? Since each of these is positive, the minimum is one of them. We don't know which one it is, right? Since each of these is positive, the minimum is one of them, so the minimum is positive. So this is now just a positive number. And we had that lemma that said if I have a positive number, I can choose an epsilon, a positive epsilon less than that positive number. We've used that lemma over and over, right? Over and over again. And in fact, you can do the same thing as long as you have finitely many positive things, right? If you have infinitely many, you're maybe in trouble because there's no min, maybe. And in fact, the inf might be 0 and you can't choose a positive epsilon less than all of them. But as long as you have finitely many things, you can always choose an epsilon that's less than all of them. Okay, and when you get into analysis, sometimes you have, several things that you're trying to choose epsilon less than. But you can always do it as long as it's finite. Okay? If you want to be concrete, remember how we proved this, right? Just take this number and divide by 2. Right?
So how do you know that s squared minus a over 2s is the min?
Is what?
How do you know that s squared over minus a over 2s is less than s?
We don't. And it doesn't matter. Right? Because we're taking the minimum of these two. So one smaller than the other, it doesn't matter because we're going to pick epsilon less than both of them. Okay? If we choose epsilon less than the minimum, it's less than one, it's less than the other. And we use those two inequalities for separate purposes, right? We use that epsilon is less than s to make sure that our calculation in the contradiction is correct. And then we used the other inequality, less than this one, to make sure that epsilon does what we said it did.
So it doesn't matter which one's greater?
Does not.
Because you know that epsilon is less than s, and you just showed that for the second one, the equation holds.
No, we're choosing epsilon, right? And we're choosing it to be less than this one, and we're choosing it to be less than that one. We don't know which one is smaller. Right. I mean, one of them is smaller, right? Suppose that one's smaller. Well, then we'll just choose epsilon less than this one. This one is less than or equal to that one, so no problem. Okay, remember we had that little, one of the first things we proved about these things, right, is that if you have two things, one is the min, one is the max. They could be equal, right? We don't know. I mean, these two numbers could, maybe, I don't know. I mean, at least from what we know now, it might be possible to be equal. You could set them equal and see if you can get an s that satisfies that, right? I mean, you get a quadratic equation, but whether it's, has a real solution, I have to think about that. But anyway, it's not important, right? Doesn't matter which one's smaller. Just make sure epsilon is smaller than both of them and you're good. Okay? Again, we had two purposes, one for each one. So we make sure epsilon satisfies both those inequalities so it works for both purposes.
Okay, and so you choose epsilon so that it's smaller than
Yep.
Because you already know that it's smaller than s.
Yep.
You pick the other one, so that way you have both of them covered.
Pick the other what?
You pick s squared minus a over 2s, since you already know that epsilon is less than s by...
Well, I mean, you have to pick it less than both of them.
So you already know it's less than s, you don't need to show that?
Well, once I write this down, I know it's less than s and it's less than that. And I know there exists some epsilon. I don't know, I'm not claiming to say what it is, although you could take the minimum of these two and divide by 2, like we did in the proof of that statement. I don't know what it is necessarily, but I know it exists. And that's enough, okay? And this is something you'll encounter a lot in mathematics. Sometimes you can prove something very concrete, like the existence of the square root, using epsilons that you never know what they are. Using the existence of things that you don't know what they are, right? You can get very, very concrete things knowing that certain differential equations have solutions, even though you can't actually find the solutions. Right? So existence can be very useful, even when you don't know what things are. Right? Any more questions about this? Very, very important calculation. We got to finish up a couple of little details, but this is the important part now, right? This is the important calculation. This and the other calculation. Yes?
Where's our contradiction?
Contradiction is over here. So once we know that epsilon does this job here, s minus epsilon squared is bigger than a, then our contradiction, which we discussed at the very beginning, right? And sometimes you do that when your proofs get more sophisticated. This is a short, easy thing, right? So you say, okay, I'm going to explain why this will solve my problem. And then you go do the long, hard calculation. Okay, and so that's what we did here. We said, well, if I can find this epsilon, then here's a contradiction I get out of it, right? As long as I know epsilon is less than s. Right? So if I have this, then I'm good. So then this calculation shows that if I choose epsilon less than this number, I have that thing I started with that gets me the contradiction. If you wanted it to be in more orderly fashion, you know, you could then say, you could skip this for the moment, come over here, and say, okay, I'm going to choose this. That gets me this statement.